You said have everybody's homework assignment? Okay. So I emailed you back your essay edits. By and large, good job. I'll address the questions in a second. So I want you, since you're not going to have TGOs due on Thursday because Thursday is when the exam is going to be distributed, and I want you to have all of your material with you. You're going to take these next 2 days and make the edits to your essays. Have them ready to go. Email them to me by Thursday. I'll probably do a cursory look over, email you back, and then post them on Thursday. I've given you directions on exactly how to post it. You're gonna say student blog, and then the title that you have, and then the first line is going to be by, and then your names, whatever order. And then at the bottom, I want you to include the link of the article that you wrote about. So, but I've indicated that and plus all the other things that I want you to do. Very common errors. I wanted you to make sure you emphasize a little more about how this impacts, modern and future technology and just society in general. Don't put in fluff. You shouldn't be doing this thing where you're trying to put in fluff to add word count. What you should be doing is you should be trying to have the wheels spin. These people are going to come in and they're going to ask you questions or make corrections. It's okay to be wrong. That's why it starts with student blog. Okay? So this is a learning experience. You're going to be with a lot of people who are going to be able to read through BS, right? So don't have that attitude towards it. Have the attitude towards this is what I think right now, and then they're going to come around and say, you may have somebody who may be the competitor of the person you're writing about, and they'll rage, and just roll with it. It's okay. This is an opportunity for you to make mistakes and be corrected by people who know what they're talking about. So definitely take advantage of that. So what you're going to be doing is you're going to be posting. You're going to be interacting with these people as they post on your blog. And then the last week, you're going to be doing a 15-minute PowerPoint presentation on what you talked about in your blog post, what you learned from interacting with everybody, and so that way everybody can get kind of a outside the scope feel for certain things that are going on currently in Cmos VLSI design. Okay. So does everybody understand these two algorithms I threw at you last class? Main test gen and then the D algorithm? Make sense? All right. So today we're going to be covering this concept of boundary scan. So from here on out, for the rest of the section, we're going to be learning about testing and so what's known as process variations. In this section, we're going to be talking about Skandhas design strategy. So what's going to happen is we're going to have some sort of chip, and we're going to have it surrounded by these things known as scan registers, right? The scan registers surround the boundary, hence boundary scan, and we're going to be testing the interconnects of the circuit by having a normal mode, a scan mode, and data in and out mode, right? So we're going to formally define boundary scan as a method for testing interconnects, wires or lines on printed circuit boards or sub-blocks inside an integrated circuit. So we'd be able to isolate modules and be able to test chips on board using this boundary scan architecture. We're going to discuss a couple of boundary architectures, but the whole idea is we're going to be using these scan registers. So you're going to have a data and an SI pin, right? You're going to have scan. It's either going to take it when you're not doing the scan, you're just loading in from data, but when you do have the scan value, you're going to be loading it from SI. That's how you're going to do your boundary scan test. Then you're going to use a D flip-flop with a clock signal, and then this output is going to be going into your architecture. So we're going to formally define scan registers as flip-flops used to provide scan design capabilities. When the scan signal is deasserted, that means 0, the register behaves as a conventional register. So, right? Storing data on the D input. When scan is asserted, meaning it's 1, that means we're going to be using this SI input, which is how we're going to be, so we're going to be using these inputs as test vectors. So previously in this section, we have discussed how do we come up with these text vectors. Now we're trying to figure out how do we use test vectors when we want to test it and then be able to just have it operate normally when we don't. So this is an important part right here. While it's not part of the TGO, this is something that's really understanding. Boundary scan is going to add area. That's the major trade-off, right? However, and it's not part of the function. What it does, though, is it provides you an opportunity to be able to test. So if you're trying to come up with a set of test vectors and you want to be able to test this in real time, you're going to be having some built-in logic blocks. Built-in logic block observer, we'll study that, also known as BILBO. I'm sure that was completely unintentional. So you're going to be also using a test clock. You're going to test it at the speeds that you want to test it at, as opposed to the internal clock, which is actually going to operate in the architecture. So here's what's happening. You have your logic cloud, and you have a set of flip-flops, and you have your scan in and your datas, right? So your scan in values are going to be propagated through the flip-flops into your architectures. And then based on that, you're going to read the outputs, and when you read your outputs, that's how you're going to determine whether or not your circuit actually works. Right? So for example, in the previous circuit, we had a stuck at 1 fault, right? So if we had this large circuit in the logic cloud, and we had some sort of we suspected some sort of stuck at 1 fault, we would run our minimized set of test vectors, we would have our scan boundaries activated, and then the inputs would come in, and then we'd get our outputs, and we'd read those outputs to see if we're actually propagating the error to the output or not. And based on that specific value that we're reading, we can then tell whether or not we need to fix the chip, how we need to fix the chip, and where we need to fix the chip. So this is another example of a boundary scan. So basically what we're going to be doing is you put in the serial data in, right? There we go. So the serial data in is going to be going through all of these serial registers like so, right? And this allows you to go through your interconnected packages through your output. And then you're going to be reading the outputs of each of these chips. So you have multiple chips, right? You're trying to build observability and controllability into each pin. And then you're going to be using this internal scan chain to access the chains for a unified test strategy. So when you have your SI, you have your SI values, and you're going to have your value that you're going to be your scan value. Your scan value goes in here. And now if you have like a quad-core processor, this allows you to test all 4 quads in an efficient manner. So this is also known as something called built-in self-test, or BIST. So if you see this, especially in, you'll see BIST very commonly in job applications. Now you can say that you know what this is. BIST is the capability of a circuit, chip, board, or system. So this is Cmos, ELA385, your board, or system is your computer, to test itself. Bless you. So we have 2 types of BIST. Online built-in self-test means actually testing during normal function, meaning it's actually doing the testing while the computer is running, while the chip's running, while the board is running. Or offline BIST, testing occurs when the circuit is not carrying its normal operation. So you switch it to offline BIST, and then you perform your boundary scan. And so for this example, I want to kind of read through this. This is a really good understanding what the pros and cons of BIST are. So the question reads, explain the principles of built-in self-test. What are the advantages and disadvantages of BIST, or BIST? So this builds on scan by surrounding logic blocks with a pseudo-random sequence generator on the logic inputs and a scan chain on the output. So now we have some sort of pseudo-random values going into our SI values, right, for our scan. Now we have our scan values. These functions, in addition to the normal operation of the flip-flop, may be combined into one structure. And so we're going to be learning about that next. This concept is called Bilbo. BIST can reduce the number of external test vectors needed if it is compatible with a system test methodology. So one way you can do this is by using your D algorithm. You can perform high-speed testing with a low-speed tester. Because remember, you disable the internal clock, so therefore you can run your own clock on the test vector. So if you're trying to test, later in the section we're going to be learning about design corners and process variations. How when you're testing NMOS transistors and PMOS transistors, they switch at certain speeds, right? So we know it works more efficiently. We have to, if we're running it slow and it doesn't work, we have a specific error. If we're running it fast and it doesn't work, we have another error. So being able to change these types of speeds while doing testing is actually important. And then the last disadvantage is it costs theory on the chip, because the built-in self-test is surrounds the boundary but does not contribute to the logical function. Does this make sense so far? I'm going to show you an example here in a minute that uses two separate control signals. Screw up a little bit here. So this type of built-in self-test that uses boundary scanning, a very common one is known as built-in logic block observer. That is Bilbo. And the whole idea is it uses two control signals, and we have, since we have four possibilities for the two control signals, we actually have four different possibilities. So 0, 0, we have boundary scan. So now we're just checking our scan, right? We're just going to put in certain values. 0, 1, now we activate our pseudo-random generated values. And so that's C0 and C1 going into here. So we have our flip-flops, and we have AND gates and logic OR gates to determine whether or not certain things are going to come in, right? So this is the drawing, which is part of the TGO. 1, 0, you're going to reset the flip-flops, and then 1, 1, you go back to normal oscillation. So let's say we want to do a boundary scan. We go to 0, 0, right? When we do 0, 0, this will allow us to here, right? Or flip-flops. So where does it go? So it goes 0 here, right? So this becomes 0. So it just becomes this value, this becomes this value, and this becomes this value, right? So the boundary scan is going to be performed. So if we go to 0, 1, though, right? So now we have a 1 on the input. So this is an AND gate with two NOR inputs, right? So if we recall bubble pushing, that's just the same thing as a NOR. Right? So we have 1 on the input of a NOR gate, so this automatically becomes 0. So 0, 1, the NAND gate's 0, so this becomes 0, 0. So the input to the D flip-flop becomes 0. With a 1, 0, 1, 0 here, right? 1 here, and now we have SI, right? It's 1, 0, and then 1, 0 becomes 0 here, so now we have a 0 on this input, and now we're trying to propagate the flip-flop, and this allows us to reset. And then 1, 1, here's what happens with 1, 1. So you have 1 and 1, 1 is selected for SI. Don't care about the loop back. 1 and so SI and 1, so it's going to be SI bar, right? 1, 1, and 1 here, so it's going to be a 1 on the OR gate, so this becomes a 1. So now we have normal operation. We operate with a clock. Propagated value from Q, propagated value from Q, and so forth. So on these outputs that are generated by the flip-flop, we can then use these to go into the logic cloud and these are separate from the actual logical calculation of the chip. We had a little bit of area. We were able to perform our built-in self-test based on our inputs from the boundary scan or from the pseudo-random generated values like D0, D1, and D2, right? So based on those values, that allows us to propagate the AND, right? So it's 0, 1, so this is 1, right? And that means this value is propagated to this output here, right? For 0, 1. So if this is 1, that means D0. If it's 0, that means the output of the AND gate is going to be 0. If D0 is 1, it's going to be 1. So now we perform our boundary scan. Same thing here, same thing here. If it's 0, that means we're not propagating the normal value. But we have to put in 1, 0 first to reset the flip-flops and then go to 1, 1 to be able to do normal operation. So this is kind of just a small token understanding of built-in self-test. For those of you watching us on the video later, that's the actual circuit. Does anybody have any questions about this before I go on to this concept of robustness? All right, so the general idea of robustness is you're trying to, you have to worry about getting billions of transistors on a cell all at once, right? And you want it to be able to work at all kinds of different speeds, temperatures, you name it. Now transistors are so small that printing errors below the wavelength of light and variations in the discrete number of dopant atoms have major effects on the performance. We learned about this in section 1. Doping the transistors, whether it's the P-type or the N-type, you have to be able to create a certain number of holes to be able to create the current flow, right? So now we hook that up through our source and our drain, and then we're hooking up transistors. We learned about stick diagrams where we have to hook up the sticks in a certain way in order to be able to get that flow to operate properly. Then we learned about capacitance and loads, right? So now we have to have different sizes on our transistors to be able to properly propagate the logic in order for us to be able to make our noise margins. Now we need to be able to do that with billions and billions of transistors on a small little chip. That concept of being able to do that consistently, which is what you all aspire to do since you're in this room, because you're all electrical engineers, something called robustness. So the first thing we're going to do is we're going to worry about this concept called process variation. So when we are synthesizing the chip, we are trying to figure out, that's the actual process, right? Process variation, the naturally occurring variation in the attributes of transistors, length, width, oxide thickness, when integrated circuits are fabricated. Now recall earlier in this, it was actually last lecture, when I was talking about some of the errors that can happen during the fabrication process. Now, when you have, a 22 nanometer chip, remember a half of the process size is your poly. So now we're trying to get all the way down to 11 nanometers, and we need to make that 11 nanometers every single time. there has to be some sort of built-in variation in order to guarantee it will still work. That's where noise margin comes into play. Because it would be great if we could just have it 0 or 1 every time, but because of these naturally occurring variations in the thickness, just because nature and nothing's 100% predictable, we have to account for that in design. So oftentimes you will see them described as PVT, process voltage and temperature variations. So process is what happens when you're actually in the actual physical chip itself. Voltage is what happens when your VDD has slight fluctuations for various reasons. Now, going back, how is a clock signal generated? You have to have some sort of voltage potential, and then you have some crystal placed on that, between that voltage, which is then going to create some sort of AC value, which then you can use an AC-DC converter to create your DC signal. So there's going to be some sort of variation on the 0 and 1. It's really small, but we still have to account for it, right? It's like, oh, it was just a small one. Okay, well, my computer still doesn't work sometimes, so I'm going to go buy a different one. These are the kind of things that we have to worry about. So this is a layout here. This is what's known as a universal distribution of, or a Gaussian statistical distribution. So we have X, Y, and variation percentage. So by and large, most of our circuits work properly, right? So a uniform distribution for VDB could be specific at 1 volt at plus or minus 10%. So that could go all the way up from 1.1 to 0.9, right? All parts should work. Now, if it doesn't, those don't look good. This kind of doesn't look that great either, right? Well, hold on, let me get rid of that. Let me zoom in on this. So you can see that a little better, right? So we have a chip. And we have some sort of voltage variation that we're measuring here, right? By and large, everything's really close, right? Except we have some small problems. A huge problem there, right? Yep. Something's wrong there. Some sort of short. We're draining voltage when we shouldn't be. Could be a variety of different reasons. Now that we've learned about capacitance between wires, we've learned about what happens if you don't actually draw the pin. You're dissipating energy into the environment, right? If you haven't properly accounted for your capacitance, you're driving too hard, you're consuming too much energy. You have some sort of variation here. Again, over here, now you're actually, somehow there's the voltage that's being presented to the circuit is too high. There's all kinds of different reasons that could be. So the question becomes, how much can we account for and still guarantee the operation of the circuit? So there are 4 different types of process variation. So we have supply voltage, tolerance of voltage regulator, the IR, so that's power, current times resistance, right? So drops along supply rails, and current over time noise, right? Remember, right? Look familiar? I'm sorry, I equals C dV dt, right? So now we have to worry about supply voltage, capacitance, and noise along on the current that's being passed through the transistor. Threshold voltage, we've learned a lot about this at this point, right? So we have to have some sort of threshold voltage in order to be able to create the channel from source to drain. Now, if you screw up your dopants in the channel, it becomes a lot more difficult, right? Because if we go all the way back, so we talk about our NMOS transistor, right? So we have a source, we have our drain, we have our silicon oxide, and we have our gate, right? Now, we have This is our N-type transistor. And what we're trying to do is we're trying to get a channel. So what we have is we put a 1 in the Cmos. This drives this down, and then we create the channel here. Now, if we don't properly dope this, let's say we make this too heavily doped, right? Or we accidentally dope this somehow with N-type. So now we're dragging stuff up into the channel, and we're not able to actually create the channel. Or if we don't dope the N-types enough. Now we don't have, we'll get cut off, or it's too easy to get into saturation. And the standard deviation is inversely proportional to the channel area. If your channel area is larger, that means it's actually making it from source to the drain. Smaller it gets, the harder it is to raise the threshold it's required. So that's why it's inversely proportional. Next, we worry about channel length. Specifically, we're going to worry about this concept called across-chip line width variation. So we have a big chip, right? And we have a bunch of transistors. So here we have LER, and this is ACLV, right? This is actually our description. So here, our cross width, so basically we're trying to make, ideally, what we want is this gray value, right? But we have some sort of degradation for the blue is what actually happens. So we're not actually meeting our DRC in synthesis. If we don't meet our DRC in synthesis, that means we're going to have problems when we actually do simulation. Random line roughness. I can zoom in on that a little more, but it's probably not as visible in class. Right? So we have a wire, and ideally you want the wire to be the same thickness all the way through, right? But if the thickness of the wire changes, well, guess what? Now your capacitance changes. And last but certainly not least, interconnects, etching variations affect your width, your height, and the size of your wire, right? You recall that diagram? So the smaller and smaller you get, the harder and harder it becomes to make this accurate, right? But the demand for chips becomes smaller and smaller because due to Moore's law, due to customer demand. Bless you. Bless you. You're going to live? No. Do you need to see a doctor? All right, so now that Adam isn't dead, we can continue. So we've talked about, so this is the whole idea of like when we are synthesizing it, this is everything that can happen with the process. Does this make sense? Especially now, this is a really good combining concepts type understanding, because now you have to understand how the transistor works. You have to understand how you're driving. You understand the process of synthesizing a chip, a whole lithography, what's going on with the dopants. So now you're going all the way from that level where you're going back to your Gansky chart, where you're down from you understand polygons, right? You draw the polygons, you represent them using stick diagrams, and then you actually have an example of polygons here. Polygons then goes to your NAND gates, AND gates, which you've then calculated. We can figure out the capacitance. Wire length has the value of the capacitance. Wire length contributes to the power consumption. So you try to make the wire shorter so that way you reduce process variations with etching. And you try to also make sure that your channel lengths are similar, because it all boils down to the process. The process is twice the length of your poly, which has a lot to do with channel. See, I promise you've learned something. So we're going to talk about this concept of temperature dependence, right? So carrier mobility decreases with temperature, and therefore, if you're not able to apply the same temperature constantly through the chip, you're actually going to have an impact on your ability to conduct carriers through the channel. So we have some mobility. This kind of equation here, which is not a TGO. This is just, I'm just kind of giving you a feel through example of what's going on. Is our true temperature, what we're expecting, that mobility, times the temperature over the temperature we wanted, right? Times the fitting parameter. So that's just some constant fitting parameter. That's going to be, it's a little outside the scope of this course. It's more of a kind of a quantum mechanics problem, determining the exact value of the fitting parameter. But the important detail for you to know is that's going to be in your spice. This is obnoxious. It's not, between Adam sneezing and me almost tripping over this wire, I think half the class is going to die today. But you can have a saturation voltage that drops by about 20% just by having a 300 to 400 change from 300 to 400 Kelvin. As you can see, this is your normal one, but as temperature increases, the mobility decreases. Your temperature decreases, your mobility increases. So you can see this is temperature, and this is your gate source voltage. And then as temperature increases, your current's going to go down. So now we've learned about process variations and temperature variations. So this is actually another good diagram. So we have a die, right? And we have different temperatures throughout the circuit, right? So it's a 1 millimeter diameter, right? And they often veil. So this one's specifically an Intel Itanium 2. So if you recall from section 5, we did like 3 or 4 problems with the Itanium 2. We were trying to figure out how this works. So that's an ideal situation where we have a number of multiplexers and we're trying to figure out precisely the delay of the circuit. Now we have an instance where the execution core, and we can tell because we have our execution core here because it's really hot, it's 100 degrees Celsius. And if you recall, we were talking about activity factor, and activity factors for ALUs are going to be significantly higher than your activity factor for memory, right? Where your activity factor can be approximately 0.2, whereas you'll have like 0.01. That causes everything to heat up because you're going to have a lot of switching back and forth through the channel. Whereas your memory, really cool, is just waiting there to be accessed. So you have to worry about, when you're synthesizing portions of the chip, what's going to be used more versus what's going to be used less, and how can you ensure that over the expected lifetime of the chip, it's going to be able to work properly. So this is an entire field, testing for process variations. So I've listed some process variations and some examples. So lot to lot, wafers processed in batches. So between the different so processed in the batch, right? You're going to have some sort of variation in the transistors between your silicon's ability to conduct, in dopants, ability to temperature variation, wafer to wafer, inner die. That means you have a die where you have a number of chips in that die, so where we sliced off and we have one die. So then you have wafers within the die, or intra-die. Now you're getting down to the chip level. This is where these are going to be, here, let me draw that. Actually, I don't have to draw this out. We have one right here, right? So you see how we have a ring oscillator frequency where we have a whole chip with a bunch of ring oscillators, right? So a die near the edge of the wafer may etch slightly different than a die in the center, causing die-to-die channel length variations. So this comes from a specific paper, which I'll cite, Nanometer CMOS an Analog Design Challenge, where they are presenting a frequency distribution. So they're trying to make, they're putting in, we have a number of different ring oscillators in a wafer. And based on the frequency, they're trying to determine whether or not this will operate within a certain temperature range. And based on the variations within the process, we can actually see this. So another type, one wafer may be exposed to an ion implanter for a slightly different amount of time, causing wafer-to-wafer threshold voltage variation. And another example, a lot processed after a furnace has been shut down and cleaned may behave slightly differently than the lot processed earlier. So this one, the previous one, has to deal with what happens if we haven't cleaned it. Do we have impurities? Okay, so process corners. So the process corner is, now we worry about our pressure, voltage, and temperature, right? So this concept of process corner means we're going to try to figure out when something works at its typical speed, its fast speed, or slow speed. So at the typical means the value at which we're expecting it to operate. If it's still not working at slow speeds, then we know some sort of, if we say it's working typically, but we slow it down and there's some issues, that means there's a specific type of fault. We're going to discuss those a little bit later. And fast, it means typically it's not able to get to specific noise margins. The process corners represent the extremes of these parameters. We'll define this formally. Process parameter variations within which a circuit has been etched onto the wafer must function correctly. So typical, fast, and slow, and this will be denoted, and we're going to be going over a table here in a little bit, how each of these process corners can be used to test for specific errors, NMOS and PMOS, etc. So next, we're going to be talking about this concept of a Shmoo plot. The Shmoo plot is a graphical display of the response of a component or system varying over a range of conditions and inputs. So this green means it's passed, red means it's failed. So here, I'm going to zoom up a little bit so you can have the Shmoo plot. But we have the X value is time and the Y value is voltage. So here we have 1.1 through 0.8, and we have some sort of cycle time. So as the cycle time is increasing, it's passing, but it's failing here. And there's actually a comic strip. I'm actually going to show you a picture here in a minute it's actually called Shmoo, and it looks like that a little bit. But this is the graphical representation. So if you're putting in a number of different voltages and speeds, and you test for all of them, and it meets the parameter or doesn't meet the parameter, this is an example of testing for a process corner. So it's slow, typical, fast, and for a set of voltages. So now we've tested our process variation for voltage over our process corners, slow, typical, and fast. I can show you this is actually where the Shmoo comes from. Right? And so there's your process variation. Everything works inside the Shmoo. Outside it doesn't work so much. And so the guy I created is called Al Cap, and the cartoon is called Little Abner, but his name is the Shmoo. So you can see kind of sort of. So you've got Bilbo and the Shmoo today, right? All right, so does anybody have any questions on process corners, shmoo plots? Because we're going to be going in, and we're going to be going into a lot more detail about how these different process corners can impact certain tests in a little bit here. So since circuits are most likely to file at the corners of the design space, this is a good way to test them. All right, so this is kind of where I was talking about here. So this is our good design corner checks. So this is where you're going to be testing for it, all right? So the 5 things we're going to be testing for NMOS, PMOS, our wire, our supply voltage, and temperature. So if we're doing timing specifications, the first thing we're going to do is we're going to test our typical NMOS, PMOS, and wire signal. And then why do you think we're going to slow down for VDD and temperature? Why do you think for timing we want to use the slow design corner? So we have, if we go too fast, right? Remember we have some sort of RC delay. Remember from section 2 we did RC modeling? And if you recall from like 235, your circuit theory course, where you're going to have a delay in rise time. If you go too fast in your switching, and we're actually going to be going over this quite a bit in section 7, you're going to get some sort of power spike, and it's not a proper representation of what's actually going on. So if you do it slow and it's still not working, you have a real problem with your circuit. And then the difference here is timing specifications conservative. We are now going to go slow for all 3 of these. So let me zoom in a little more so everybody can see all of the chart. Is that better? It's better? Okay. So race conditions, hold time constraints, pulse collapse, and noise, right? So now this should intuitively we want everything to be fast. We're trying to test for race conditions. We're trying to test for hold time constraints. If we go too fast, does it overrun the hold time, right? Pulse collapse and noise. So for dynamic power consumption, here we have VDD as fast and everything else is slow. Why do you think that is? I'll give you a hint. Think back to your dynamic power consumption equation. This is a TGO too, and you did this on exam 1. What's the equation for dynamic power consumption? Yep, VDD is part of it. VDD square is, in fact, part of it. Times frequency. One more. Giving you a giant hint here. Load capacitance, right? Load capacitance times VDD squared times the frequency. So if you're trying to test your supply voltage, where you're not going to be able to meet it is when you have a higher frequency, right? So if you're going to test the fast supply voltage for dynamic power consumption, everything's going to be fast. Everything else, NMOS, PMOS, is going to be like timing, right? What? That is a good question. Why is dynamic power listed as question mark for wire? So you've asked me. Now the tables have turned. I'm asking you. This is a good grad student type question, but it's also a good extra credit type question for undergrads. Why is dynamic power listed as question mark? Why would we not exactly know? What's going on with wires that's different than your typical transistor? I'll give you a hint. I want to see if you guys can actually figure this out, especially since I guess everyone's tired and it took us about 30 seconds to get the equation for dynamic power consumption. Which, by the way, when you do an interview and you're asked the equation for dynamic power consumption, I highly recommend that's an immediate answer. 1/2 CL VDD squared times frequency. So this is a good research thing for you guys. Sub-threshold leakage. We want everything to be fast. However, we want temperature. If we're trying to test sub-threshold leakage, we want it to be slow. Racing of gates against wires and racing of wires against gates. Now notice something interesting. These are slow and these are fast. So here you have your wires are the opposite of your VDD. And this is a hint for those of you looking into this over here. This is a massive hint. When you want it slow, you're racing of gates against wires. That means our wires are going to be fast and our gates are going to be slow. Now, if we're rating wires against gates, this means we want the gates to be fast and the wire to be slow, and we want to see if we can still make that. And so you see that the VDD in temperature matches the gates, but see how it doesn't match the wire? Yay! All right, turn off. That's another hint. And you learn sufficient information in section 5 to be able to figure this out. So, again, we learned also in section 5 about pseudo NMOS and ratioed circuits. And so we know that PMOS, we want it fast because we have one PMOS transistor, right, in all these. And NMOS, we want to run it slow because we have a number of different transistors to represent the logic. And again, just like before, we want these values to be fast. And again, if we're trying to do race of NMOS against PMOS, we want NMOS to be fast. Here, we want NMOS to be fast and PMOS to be slow. So we want our PMOS circuit, we're going to apply some slow value to it, and then we're going to have a race condition with our pull-down network for PMOS. So this kind of sort of makes sense. If you are trying to find out any kind of testing, this is a very good chart to have on hand. So we have to test for a number of things. We have come up with a chip. We need to make sure it works to certain design constraints. We need to make sure that it meets timing specifications. First, we want to make sure it meets the ones that we say works, right? So that's called our bin parts. So we have typical, and we slow it down for VDD and temperature. Timing specifications conservatively, we slow it down even further just to see, we check to see if there's some reason it might not be working when it's running slowly. Race conditions, we have to test for all the race conditions in the circuit. We have to test our hold timing constraints, especially for flip-flops and latches, as we learned in section 5, right? So we learned about all these hold times, and we have to make sure that everything is met, time borrowing, and all these pulse types of noise. For dynamic power consumption, we run the NMOS and PMOS slow. We have our VDD fast because of our dynamic power. The temperature is going to also be slow. And wires are going to be question mark for a specific reason. Does anybody have any hints, any ideas about that?
Just because the distribution of wires, like using it for VDD, it's going to differ between using it between the NMOS and PMOSs.
Mm-hmm. But think about specifically which one. You're on the right path. But specifically dynamic power. What is it about? What does dynamic mean? What's happening when we
Switching the paths.
Switching, right? Ooh, there you go, Terrence. And what's the term? What's the specific factor for direction? What is the
Activity factor?
Not activity factor.
Switching factor.
There's some sort of switching factor for the directions of the wires.
1 and 0.
Yep, that's it. You're thinking of it. Miller coupling factor. There you guys figured it out. The Miller coupling factor has a lot to do with this. Because in the same direction, they switch in the same direction, you can test it fast. But if you switch in the opposite direction, you have to test it slow. Good job, guys. You figured it out. See? I told you guys knew how to do this.
Is that extra credit for all?
Remember that on your exam. But I will expect you on an exam to justify that with math and things. Okay. But that's the general overview. It's like, see, I told you, you guys have the general understanding. And the reason why this is a good thing for you to do, even though it's extra credit, is because inevitably when you're in an interview, you're going to be asked a question where you haven't learned it at the University of Mississippi in class, but you've learned all of the pieces. So I encourage you to challenge questions like this. Why is that? Well, have I learned everything I need to know? What's going on? I know dynamic power consumption. I know the concepts behind wires. I know that there's not actually a supply voltage, but I understand that there's coupling capacitances that have an impact. I understand that if it's going in the same direction, it has a different impact than if they're going in the opposite direction, or if one's switching and the other one isn't switching. So because of that, you have to account for all kinds of different things when accounting for wires. Now, typically, you're going to be doing that in your races. That's why you wait with typical when you're dealing with pseudo and ratio circuits. Fast with race conditions because you want to be able to meet everything else because the wires are the paths for the race conditions. And then you want to stick with the timing constraints for PMOS and NMOS for your circuits. So now does this table make a lot more sense? This is specifically why we choose these process corners. By choosing, and one of the best things about process corners is it allows you to pick a fast value or a slow value that you know is on the corner of an extreme. And if it's not meeting that, you've narrowed down potential problems. And so I want to combine some concepts here for the rest of this particular section. Example 6.7. A circuit does not operate at the desired frequency. Uh-oh. Cooling the circuit with freeze spray fixes the problem. We've cooled the circuit down, and now it works. Schmoop plot shows the circuit operates correctly at higher than normal VDD. What is the general nature of the likely problem and why? So we kind of go back here. So if you cool the circuit, we're improving the transistors, we're improving the mobility of the transistors, right? So we're improving its speed. Raising VDD has the same effect, right? Dynamic power consumption, VDD squared. These two tests probably point to a path that is too slow at normal temperature and voltage. Resimulating the path to ensure all parasitics, especially at the slow process corner, should reveal the problem. So here we have some sort of slow wire, right? Pointing to a path that is too slow for normal temperature and voltage. So we tested it slow, right? We have some sort of timing off, or we're having races of gates against wires. So by just doing those two simple mental observations, we've narrowed down our potential problems, right? So then we can then use our boundary scan, we can use our test vectors, we can use our D algorithm. Specifically, if it's not meeting timing, we probably need to go back and check on our issue is at a level below in our actual foundry. So does that make sense? 6.8. So recall at the end of, so in section 5, I had a number of we had a number of sequential circuits. We had a pass transistor. We had a switch. We kept adding on portions to deal with certain problems, right? So this is where this is a really good combining concept type question for this. So we have a 2-to-1 mux here, right? And we just have NMOS transistors. Now here's the issue. The mux works when S is 0, right? But not 1, which means it's not for D1, right? So if it's 0, that means S bar is going to be 1, so this works, so D0 works fine. But when it's 1, it doesn't work. That means we have 1 and 0. Additionally, it fails at lower VDD, and for NMOS and VDD and temperature, it fails in the SFSF design corner. What is the general nature of the likely problem and how would you fix it? So that means we have an instance where it's not 1 and 0. Additionally, we have some sort of lower VDD, right? So we can kind of right off the bat narrow it down to some sort of NMOS transistor, right? When it's not working at lower VDD, that means X is never getting to the rising above VDD minus VT. So the whole idea of our NMOS transistor is we are putting 1 on it so you can pass from ground to the output, right? So what do we know about, thinking all the way back to section 1, what do we know about NMOS transistors? They're good conductors of 1s, and they pass 0s through, right? What are they poor at passing? 1s. Correct. So what change did we make to this circuit in order to account for that? How did we fix this back in section 5? We had to make some addition to the circuit. If we have an instance where we're not able to pass 1s, no, not invert it. So let's say I have a path here, right? If I have an NMOS transistor, right? If it's going to be 1, that means I'm able to pass 0s, right? But I need to be able to pass 1s through here as well, right? So what would I want to do? Add a PMOS, so we can add a 0, it'll pass 1. So now we've gone from just a transmission gate to the transmission gates here to a pass transistor gate. So now we've caused that fixed that problem. Now this not being able to get down here, the other hint is the failure at the temperature corner. So the temperature, right? 1, 2, 3, 4. That means the temperature is not working when it's fast. Now recall body effect, right? Body effect is affected by the temperature because it affects the mobility. So we know that when we switch it, we're not able to get the value all the way down, so it's not properly working. So we have some sort of noise at X because the body effect is impacting this transistor. So therefore, to eliminate that problem, because of the fact that when D is 1 is on the input, it's not passing anything, we add a PMOS transistor to fix the problem. So that means we now have added a PMOS transistor and PMOS transistor here. We hook those up to S and S bar appropriately, and that allows the circuit to work better. Okay, so 6.9. Consider the pseudo NMOS OR gate that we have here. Right? So we have pseudo NMOS, NOR gate, and then an inverter. When only A or B our input is 1, when only A or B is 1, it puts a 0 on the output. So if you have a 1 here, or 0 and 1, puts a 1 on the output. For NMOS and PMOS, this happens in the SF transistor. So what are we wanting here? If it's only 0 or only 1, if only one of them is 1, so that means we have a path, right? So it should be 0. So if we have a 1 there, right, then there should be a path to 0. Meaning a 1 is on the, puts a 0 on the output, meaning 1 is X. So you have some sort of 1 there, 0 there. So that's the error. We should have an instance where we put a 0, we put a 1, right? Now what we notice is it only happens when one of them is 1, not both. If both of them are 1, we get the correct 0 on the output. Now think back to pseudo NMOS. We had a huge problem detailing saturation mode and linear mode, right? Why did we have to think about that? What's the issue with pseudo NMOS that we have to consider in these designs? Gate size, why? Well, let's think back. What is the operation of the PMOS transistor happening in pseudo NMOS? What's on the gate? Ground. So what does that mean? With a 0 on the gate of a PMOS transistor, it's always on, right? So what are the two modes that pseudo NMOS operates for that PMOS transistor? If it's always on, that means we never have what? Remember we have 3 ranges for that transistor can operate in.
So we never have cutoff mode?
Yeah, so we have no cutoff mode. So we have to worry about the PMOS transistor operating in saturation while the NMOS transistor is operating linear. So if we have an instance where when only one of the NMOS transistors is on, and we're not actually, and we have this instance where we're trying to get this to be 0, which should be 0 but is 1 and 1 on the output, but what we're actually getting is a 1 here and a 0 here. What does that mean? Yep, we're passing the PMOS. Yeah, we're passing the PMOS to the output instead of the NMOS. And so going back to what Jason said earlier, what does this mean we have to do to our NMOS transistors? Just repeat the original answer you had.
Change the size.
Changing the size, right? We have to worry about sizing because if only one of them is on, that means we aren't doing well enough to pull down to 0. So we have to change the transistor size in order to properly accommodate for that. So we have this is a result of improperly sized NMOS transistors. And as you can see, if you can go back to example 5.3, that is a perfect description of what the issue is. So this should hopefully, now we're using our design corners to figure out why we made those designs in section 5. So this should be tying, everything should be starting to tie together now. So I'll read it formally. If only A or B is 1 in a pseudo NMOS transistor and PMOS is switching faster than NMOS, This means the NMOS gates are not properly ratioed so that the NMOS can bring the gate down to 0 on the output. Therefore, fix the ratios of the NMOS and PMOS transistors akin to example 5.3. Let me read the exact answer for the previous question too. So we had this, we didn't have our PMOS transistor, so while it's not working at lower VDD, that means X is, never rises above VDD minus VT, but one NMOS transistor and the other is not. It is also failing in the slow NMOS corner. The other hint is the failure at the temperature corner. That means the surface potential, or VSB, source base, at threshold voltage has been affected in the D1 NMOS is affected by thermal voltage. This is body biasing. So if you go back to your body biasing equation, you'll see that all of those are tied in. CMOS designers use transmission gates instead of pass transistors to counter this common problem. We have, and so this is going to be the last question that could be covered in exam material. And this will be good because we'll finish this up and we'll just do the homework assignment. Will be everything through section 6, but it's not due. You'll just have this as your reference. Example 6.10, consider the CMOS latch shown. So we have a latch here, we have an inverter, we have a phi and phi bar, and we have another inverter on the output. A fault occurs when Q is equal to 0. When phi is set to 0, that means phi is here, and phi bar is 1. The circuit will spontaneously flip to 1. D doesn't change, that means our input, but we still have this flipping from Q, the circuit will flip from 0 to 1 on the output, right? So that means 1 is on the output here. That means we have 0 at X. That means since it's flipped, that means previously we had 1 at X and 0 on the output. But it just flips. We haven't changed anything. Why do you think this is? Without looking at the solution. Let's look at the circuit for a minute. So here's our condition. We have 0, that means phi bar is 1. And we have some sort of value where it's initially 1, right? And then that means our output should be 0. And then what happens is this spontaneously flips to 1. That's what the problem states. So now we figure out, why is this happening? Well, the first step is we troubleshoot back to X and we know this is 0. So that means at some point this combination is causing the capacitance here that's supposed to be driving this this inverter to lose its charge. So what is interesting about this particular setup for the PMOS and NMOS transistors?
The PMOS is pulling down.
PMOS is at 1. So you have a 1 on the input of the PMOS, and you have a 0 on the input of the NMOS. So what does that mean about these transistors? Both off. Exactly right, Aaron. They're both off. So we've turned off our transistors, and we initially had 1 here, so we initially had some sort of capacitance, right? And it was initially flipped, but then it spontaneously flips. So what's actually happening there? Think back to RC models. We've lost our charge, right? We had capacitance here, but you're right. The thing is that we lost the charge here, which means we're putting a 0 in to the PMOS, which means we have charged. So you're correct on the output pin. We've charged this output. So that's why it flips from 0 to 1. So that's exactly what I'll read this formally. When phi is equal to 0, the PMOS transistor has a 1 and the NMOS transistor has a 0, so they are both off. So Aaron, you are correct. If Q is 0, this means that X is 1. This means that for Q to stay at 0, X must stay at 1. But since it is spontaneously flips to 1 and X is flipping to 0, this means X is losing its charge since the gate is off. So this last, remember this design here in section 5? So what's happening is when we have this instance of 0 and 1, we now have phi is flipped. So that way this inverter is on when this transmission gate is off. And when this transmission gate is on, this inverter is off. That means when this inverter is off, we just propagate to the output. When this inverter is on and this transmission is off, it is constantly recycling the value. So we gain some area, but this allows us to maintain that value so we no longer have that spontaneous flip. So this is the end of section 6. This is also the conclusion of everything that we covered on the exam. Email me your updated essays by Thursday, and then I'll probably, 1 second, I'll give you my quick edits back, and at this point, once you see everything, you'll be able to make the edits and have them by Thursday. I'll probably just give you a quick thumbs up. I'm going to post on Wednesday on SemiWiki saying, hey everybody, the students are coming on Thursday. They'll expect them about 5 p.m. So if you could post it by 5 p.m., I'd appreciate that. And then just follow the directions. Adam, what is your question?
I was going to see if you could send the email, the thing to me again, because it only came in it looked like HTML. It was all scrambled and didn't have the actual attachment.
Okay, that's something you can ask. Okay, I'll figure that out.
Thank you.
All right. Any other questions? Okay. In that case, class is dismissed.